So what is up, everybody? How are y'all? Yeah, so this week we're going to go over section 5.4, and I hope to get through 5.6. When I was looking at the calendar, we are apparently in week 13, not week 12 like I thought. So that means there's 3 more weeks left of the semester. Finals week is the second week of the semester, so the week after Eid. Having said all that, let's get into some of this. So starting with section 5.4, I thought we should start by just considering 3 different graphs. So this first graph is the graph y is equal to x. The second graph is y is equal to 3 over 5 times x. And the third graph is 1 over 5 times x. So slope of 1, slope of 3 over 5, slope of 1 over 5. Now, I want to ask a question. Between x is equal to 0 and 5, what's the area underneath any of our lines up to the x-axis? So what's the area through here?
Is that the growth rate?
The what?
Like where your company is currently running, where their profit margin?
You're actually on the right track. There is relationship there. But no, what I'm asking is, what's this area? Just the area underneath the line up to the positive x-axis. Between 0 and 1, 2, 3, 4, 5. What's that area? Well, let me really quickly turn off. Well, if we really look at it, if we really consider it, what we've got here what I'm asking, let me actually draw it out. What I'm asking is, what's the area of this triangle? That's what I'm really asking, right? Well, we know the area of this triangle is going to be 1/2 x times y, right? In this particular case. We're going to say that, and maybe I should actually write it as L and H. Like that. Yeah, agreed? Well, so what we're saying then is that when y is equal to x, y is going to go from 0 to 5, right? And the lengths are going to be 5 by 5, right? At y equal to 3 over 5 times x, y is going to be 0 to 3, and the lengths are going to be, or the bottom leg is going to have a length of 5, so it's going to be 5 by 3, right? And then finally, 5 by 1 in that small case. Makes sense what I mean? Okay. So the areas then are going to be 1/2 times I squared, 1/2 times 15, 1/2 times 5. Now, looking at this makes some sense, right? What we've essentially got is a really small or a medium-sized triangle here, right? Small triangle here, a really small triangle here. The area is going to be 12.5 in that first case, 7.5 in the second, 2.5 in the third. What do you notice about this? Well, one thing we can notice is that we can rewrite our area function to be 1/2 times L times ML, right? That's Y. But if that's the case, then our area function is M over 2 times L squared. Does this look familiar? What's it look like?
Should look like y equals mx plus b.
It does a little bit, right? And there's a reason for that.
It's a slope intercept.
Exactly. We're using slope intercept form. So we're saying in all three of these cases, the line was an equation of this form. Now we're saying that the area is an equation of this form. Where L is just the change in our leg length, right? Our base. So here, L is just the change in our X value, right? So notice if we, for just a moment, put a pause on this, instead of rewriting this with delta L, we think of this as X. Then we would have M over 2 is equal to X squared. But isn't that the integral of mx dx? Moreover, notice that the area of this thing is somehow related to the slope of the line too, right? Together, these two things tell us something. First, integration tells us something about the area underneath the curve. Second, the slope or the derivative of a function is somehow related to the area underneath a function. And this kind of makes sense when we look back at those graphs we just had. The less steep the graph, the less area it's going to be underneath it, right? So somehow the derivative is related to the area, and the area is going to be found using an integral somehow. Now, let's step back even further. Well, not even further, but step back just another second. We said here L is equal to delta X. So somehow we're going to need to say, let's get from this to an L, to delta X. Well, I want to point something out really quickly. We could rewrite this as m over 2 x2 minus x1 squared. This is equal to m over 2 Actually, it'll be easier if I go this a slightly different route. Yeah, it'll be a lot easier if I go about this a slightly different route. So what this brings us to is the definition of the definite integral. The definite integral says, you want to get the area underneath the curve between two x values? Take the integral, and then you evaluate it at b, and subtract the integral evaluated at a. That gives you the area. So what does this mean? What do y'all think this means here? What is all this notation doing? Well, if f of x is equal to the indefinite integral of f, then the definite integral of f, this thing is just saying, evaluate your integral. Let me write it using other notation. Evaluate your integral, then plug in b, then plug in a, and subtract the 2. That is all this means. Does that make sense? So this notation is just a placeholder. What this notation is saying is do the integral, then evaluate it at b, and evaluate it at a, and take the difference. That's what this one square bar means with the superscript and subscript. And that is what this integral means with the subscript and the superscript. Make sense? So having said that, looking at another example, we've got 2x. We want to know what the area is under the line 2x equal to y, between x equal to 0 and x equal to 2. So we're going to take the area of this triangle, right? Since we know the equation of this line, we can evaluate that in the integral, right? We can say, all right, cool. Do the integration on 2x. Thing's going to come out to be 1/2 times 2 times x squared, right? So doing this, working this entirely out. Zero to 2x dx. This is going to come out to be, the integral of 2x is going to be 1/2 times 2 times x squared from 0 to 2. Well, we can simplify this to be x squared from 0 to 2. So this is going to be 2 squared minus 0 squared is equal to 4. So really, all we're doing here is combining everything we've done up to this point, as far as the integral is concerned. We're combining the integral, and we're saying let's evaluate it at 2 particular points and take the difference between those 2 evaluations, right? So this brings us to what's called the fundamental theorem of calculus. The fundamental theorem tells us that the area of a curve up to some value b is going to be the integral between a and b of f of x, which is the difference between their integrands, evaluated at b and evaluated at a. More particularly, more precisely, what the fundamental theorem of calculus tells us is that the integral from a to b of f of x dx, what this thing's going to evaluate out to be is whatever our integral evaluates out to be, our indefinite integral evaluates out to be at b, minus what it evaluates out to be at a. Does this make sense what I mean? Yeah. Now the catch here is that f has to be non-negative and continuous on the interval a to b. Now think about what that might be. What is it we're saying there? What's happening here is that we are taking small slivers of area, and we'll go over more of this derivation later. But what's happening here is we're taking small slivers of area underneath the curve, making the width of them go to 0, and adding them all up. So this idea here is actually an application of the limit and adding up a bunch of different things. And the reason why we have this idea of f being non-negative and continuous, well, we go back to here, evaluating now from 0 to a negative value, it's going to tell you the area here. This thing's going to come out to be negative. So it's not really the area, it's what's called the signed area. And that's why they have the statement that f is non-negative. We can evaluate an indefinite integral for negative values, but it won't tell us something about the area. Make sense what I mean? And that's what they're trying to get at with this non-negative definition. So again, f is non-negative and continuous in the closed interval. Cool. So the basics of all of this, if you're looking up at the board and wondering, wait, where the hell did that C go? Because that would be a good question. The basic idea of all of this is, yeah, we still have this C. But when we take the difference of our answer evaluated at B and our answer evaluated at A, well, those C's are going to wash out. They're going to cancel. Because they cancel, it comes out to be just this. Yeah. Hence, the fundamental theorem. So now checking out some properties of the indefinite integral. Hey, it's literally almost all the same properties, except for one big one, or two big ones rather. A definite integral evaluated from A to A is always going to come out to be 0. We can see that up here. If we were to say 2 to 2, well, look what happens. We're just evaluating from 2 to 2 the same value twice and subtracting it. So of course it's going to be 0, right? And if we flip the direction of our integration, so if we go from 0 to 2 to 2 to 0, and we get the negative. So the order of our index tells us something too. From A to B tells us that we're going to subtract what happens at B. I mean, my mistake. We're going to evaluate what happens at B and subtract from it what happens at A. Cool with that? Yeah. Minutes. All right, so in this first example, we want to find the area between 1 and 2 under the function x squared minus 1. So we're trying to find that area. What's the integral of x squared minus 1? 1/3 x to the third minus x, right? Sometimes you'll see me just write a bar like that. Same idea. I'll do that usually if I'm already using square brackets. I'll write just a long bar with a 1 and a 2. So this is telling us we want to evaluate this at 1/3, 1 cubed minus 1. My mistake, I meant to write 2, not 1. 2 minus, sorry about that, everybody, minus 1 cubed minus y. Like that. And this is an easy mistake to make, right? This order thing. We could easily end up with some negatives in here just by plugging these values. We just have to remember, yes, this is technically coming first, but we're evaluating this first and then subtracting this. You know what I mean? So this is going to come out to be 1/3 times 8 minus 2 minus 1/3 minus 1. And we can do the rest of the arithmetic here and solve for the exact value. The exact value would be 4/3. Now, notice here, they just use the rounded bracket. Again, a lot of different notation is going to show up for this. The whole point of it is to say, if you see the subscript 1, superscript 2, what we're saying is we want to evaluate, excuse me, the difference from 1 to 2, where we take 2 to be the thing that happens first, 1 to be the thing that happened, or 2 to be the thing that happened second, 1 to be the thing that happened first, right? This is really easy to make mistakes with. So let's check out some more problems. What about this example? Here we're going to find the area underneath this curve, 4t plus 1, that quantity squared, between t equal to 0 and t equal to 1. So first, let's just look at what the graph of this thing even is, so we can kind of understand what it is we're looking for. We're looking for the area underneath the curve, 4t plus 1, the quantity squared, where x is equal to 0 to 1. So the area we're going to get is the area of a shape like this. So what we're going to do, we're going to take the integral for t plus 1, that quantity squared, dt. What's that integral? We're going to have to apply u sub here if we want to do it. Or we can evaluate out what this entire integral is going to come out to be, right? Like we could actually evaluate out what 4t plus 1 is. I meant to say integrate that integral that last time. This is going to come out to be 16t squared plus 8t plus 1. So we could use u sub, or we could just evaluate the integrand. In this case, since we're already going to have to do a lot of work, let's do this. Let's just plug it in for now. 0 to 1, 16t squared plus 8t plus 1 dt. This evaluates out to be 16 over 3 t cubed plus 4 t squared plus t from 0 to 1. Notice they just went ahead and used u sub themselves. They say we should get 31 over 3 here at the very end. So just to prove a point that u sub and this expansion are equivalent, we've got 16 over 3, 1 cubed, plus 4 times 1 squared, plus 1 minus, well, with all the zeros in it, it's just going to be 0, right? 16 over 3, 0 cubed, plus 4 times 0 squared, plus 0. It's going to come out to be 16 over 3 plus 4 can be rewritten as 12 over 3 plus 1 can be rewritten as 3 over 3. So this thing comes out to be 31 over 3. Everybody cool with this? So what we're doing, we're first evaluating the integral, and then we're taking the difference between the integral evaluated at 1 and at 0. Yep. All of our old methods work here as well. So we could use u sub, or we could expand things out. Cool? Yep. So, in the case of A, ignoring our bounds, what's our integral going to come out to be? Should be 1/2 e to the 2x, right? We're going to evaluate that from 0 to 3. Here we should get the ln, and here we're going to get -3 times, what is that? 2 over 3 times x to the 3 over 2. So I'm going to jump really quickly for the sake of time. Evaluating the integrand without the integral, without concerning ourselves with the bound. That's the first thing we want to do. We're going to get 1/2 e to the 2x for that first case. So what I am saying is 0 to 3. e to the 2x dx. The way we want to evaluate these. So I'm saying ignore in quotation because we're not actually ignoring them, right? What I'm saying is we want to evaluate e to the 2x dx and then worry about our bounds, right? So we can think of it this way. Do the integrand first, or the integral first, and then concern yourself with the bounds. So now, the second step, we want to actually include our bounds. We want to say, all right, evaluate this thing, 1/2 e to the 2x from 0 to 3. Evaluate this thing at 3. And subtract from it this thing evaluated at 0. So this is going to become 1/2 e to the 6th minus 1/2 e to the 0th. So this thing is going to evaluate out to be just 1/2, right, on the right. Because e to the 0 is 1 times 1/2 is just 1/2. So this thing comes out to be whatever 1/2 e to the 6th minus 1/2 is. Notice they went ahead and pulled out the 1/2. It actually did that calculation. I have no clue what e is to the 6th power, because e is an irrational number with a non-repeating, non-terminating decimal, and I don't care to even try to do that calculation in my head. So they tell us that it comes out to be something like 201.21. Doing the second problem, like I said, evaluate that integrand, right, or that integral, I mean, comes out to be the ln, then apply your bounds, and do the arithmetic or algebra accordingly. So really, this isn't a whole lot of new stuff. It's more just applying the old stuff, right? Applying the integral with 2 extra steps in here. Really, not even 2 extra steps, just 1, right? So having said that, what time is it? 13? Okay, yeah, we can get through. I'm trying not to like run through too many examples and get too far ahead. Because I want to spend some time thinking about some of this stuff first. So, in particular, let's think about this example here. This example is a great one for just general thought process. Yeah, I know what I'm trying to say. It's too damn early. That's what I'm trying to say. Okay, how are we gonna do this? How do you integrate the absolute value of something? What even is the absolute value of a thing? It sucks is what it is, right? Like, who wants to do this? That looks ugly, but it's not as bad as it might look. So, crash course in what the absolute value of a thing is. The absolute value of a thing is saying we're going to break it up into two parts. We're going to say whenever this thing is positive, keep it the same way. Whenever this thing is negative, take the negative of it, right? So the absolute value of this is going to end up being 2x minus 1 is equal to 2x minus 1 when 2x minus 1 is greater than or equal to 0, or negative 2x minus 1 when 2x minus 1 is less than 0. And what this integral is asking for is for us to find this area and this area and add them together. Now I tell us to be careful here because this in particular, whenever you see a piecewise function, tells us you're going to have to break up the problem. We're going to have to be really careful with how we break this up. What we need to worry about is when this thing is equal to 0. So what we need to do then is, let me write all this out. What we need to do is we need to first find when 2x minus 1 is equal to 0. Okay, well that's like finding when 2x is equal to 1 or x is equal to 1/2, right? So the integral from 0 to 2 of the absolute value of 2x minus 1 with respect to x, this thing's going to get broken up into two parts. 0 to 1/2 dx plus 1/2 to 2 dx. Okay. Now we need to break this up for two different reasons. One, I shouldn't have said it that way. We need to break it up for really just one reason. This line has a different equation than this line, right? So for this first part, we need to consider negative 2x minus 1, right? For the second part, we need to consider 2x minus 1. Make sense? And now that we've broken up our integral, we can actually evaluate this thing. We can find the area underneath this curve. Everybody cool with that? So the real reason why we need to break this up is because what the absolute value is doing is defining a function in two parts. It's a piecewise definition. And it says, take the negative parts, make them positive. Take the positive parts and leave them just the way they are. So because we have really two functions inside of one, we have to evaluate the one part and then the other part. Cool. And that's why the integral has to be broken up this way. Here I should have noted that. So, jumping to the actual evaluation. Because again, this is two different functions embedded into one. We have to break up this integrand, two different parts. We evaluate this first part from 0 to 1/2, the second part from 1/2 to 2, and calculate accordingly. Everybody cool with this? So again, this really isn't a whole lot of new material. It's more about how do we use it? Where does this stuff get applied? And it just so happens that through it, we discover there's a cool relationship between area and slope. Having said that, y'all are free to go. When we come back to this problem next class at the very beginning, because I think this is one that we should take some time to understand. But like I said, y'all are free to go.